I forgot to record. Really quickly, I'm going to bring the people at home up to speed. We learned 4 rules for derivatives. The first rule we learned was that the derivative of a constant is just 0. So if we have a number and we want to do the derivative of a number, we get 0. The next rule was that the derivative of a linear function will just be the slope of that function. The next rule was that the derivative of a sum of 2 functions will be equal to the sum of those 2 derivatives. And the derivative of a constant times a function will just be equal to the constant times the derivative of that function. So if you're at home right now, I would invite you to pause the video and take a look at each of these rules and try to justify for yourself in your mind why they might be true based on your knowledge that the derivative represents the instantaneous rate of change of a function. Okay. So now we're going to do some examples, okay? So we're going to actually try to apply these rules, and we're supposed to differentiate these functions. Now, differentiate just means do the derivative of. Okay? It's kind of like the verb version of the word derivative, okay? So differentiate means do the derivative of. So who can help me with A? Which of my 4 rules do we think we're going to use to do the derivative of this function f of x equals 175? Yes? Yeah, we're going to use the first rule about the derivative of a constant because 175 is just a number. So if we want to do the derivative of that, what am I going to get? 0. Very good. So I would write f prime of x equals 0. Sweet. Next up, let's try f of x equals 19x. Which of my 4 rules, or maybe I need multiple rules, I don't know. Which, if any, of these rules should I use to do the derivative of 19x? Yes? Yeah, we should use the second rule, right? The second rule says if I do the derivative of a linear function, I just get the slope of that function. So what's the slope of this function?
19.
Yeah, slope is 19. Right? This is just mx. Our b is 0 in this case. So we've got mx plus 0. So I'm going to write f prime of x equals 19. Okay, next up I've got c. I want to do the derivative of this function, which is 2 plus 6t. Which rule or rules should I use? Yes?
Would it be the same rule as the last problem?
Yeah, we're going to use the same rule as the last problem.
So it would be 6.
Exactly. Yeah. All we do is we know that this is a linear function. The only thing that's changed now is we're using a different letter. We're using t instead of x. But this is still a linear function. I can tell that it's linear because it's in the form of kind of like mx plus b, except they just kind of switched it around a little bit. But that doesn't bother me because I know that a plus b is the same thing as b plus a, right? Whether I do 5 plus 6 or 6 plus 5, I still get 11. So switching up the order doesn't mess me up. I know that f prime of t is just going to be equal to 6. All right, come on, d's easy. It's another gimme problem, right? It's the same as the first one. Negative 2 is just a number. If I do its derivative, I'm just going to get 0. All right, another linear function. F prime of t here, again, just going to be the slope of this function. All right, now we got a tricky one. F. G of x is equal to 25x plus pi. And the question that I'll ask given the rules that we know about derivatives so far, is it possible or not possible for us to do the derivative of g of x equals 25x plus pi? How about hands up for we think it's possible? How about not possible? Anybody? Okay. It is possible for us to do the derivative of this. And the key trick here is to recognize that, you can't fool me. Pi, I know that pi is just a number. So this just looks like 25x plus a number. Okay? It's in the case which is covered by this rule here for linear functions. Okay? This is just a line with slope 25 and y-intercept pi. So I would, if I was going to graph it, I'd move up to like 3.1415, whatever. That would be my y-intercept. And then I would draw it with slope 25. So what's the derivative going to be?
25.
Just 25. Perfect. What have I done? Go away. 25. Sweet. Now let me take a quick break and ask, are there any questions about these 4 rules we've learned so far, or any of these problems we did to practice them? Pretty standard stuff? Okay. The next thing we're going to learn is the power rule. If you've taken a calculus class before you got to this class, this is probably your favorite rule and the one thing that you remember from that class. So what the rule says is that d dx of x to the power n, where n is some number, so n is some real number that's not 0. Some real number that's not 0. Okay, then what the power rule says is that the derivative of x to the power n is going to be equal to n times x to the power n minus 1. So what have I done here? I took the power and I brought it down front and multiplied. Then I took that same power and I decreased it by 1. Okay? So if we want to see that in action, we can do the derivative of x to the power 8. I know that I should just bring that power down front, so I'll write 8 first, and then I'll have x, and the power should be 1 less than it was before, so it should be 7. So that's f prime of x if f of x is equal to x to the power 8. Any questions about the power rule? Great. Well, let's do some examples. Let's do D first. We'll start on D. Who wants to help me do problem D? Can I have a volunteer? All right. I'm going to ask you some questions. I want you to answer them, okay? Is it a problem that the power's 4.5? No. That's right, because n is just some real number, okay? So long as it's a number that's not 0, we're good to go. So we can apply the power rule here, okay? There's one other rule that I have to use, and that's going to be this rule up here, which said that the derivative of a constant times a function is just going to be equal to the constant times the derivative of that function. So, first of all, I know that d dx of 2 times x to the 4.5 will be equal to 2 times d dx of x to the 4.5. Now, sir, can you help me complete the inside of this? If I want to do the derivative of x to the 4.5, what should I do?
So we should do 2 times 4.5 to get 9.
Yep, 2 times 4.5.
And then x, and then in the exponent it would be 4.5 minus 1.
Exactly. So the exponent should now be 1 less than it was before. If I start with 4.5, take away 1, I think we can all agree that that'll be a 3.5 power. So altogether we get 9x to the 3.5. Sweet. Any questions so far? Okay, so we had to use 2 rules there. We used the power rule and multiplication by constant rule. The calculus students that I've seen that are the most successful are the students who can look at a problem and decide before they get going which rules they're going to need to apply. It's a really useful skill to be able to look at this function here and say, aha, if I want to do the derivative of that, I know I'm going to need to use the constant rule because I see a constant being multiplied out front, and I know I'm going to need to use the power rule because I have x to some power. Learning that process is going to help you out in the long term. All right. Now let's do part B. I've got 1 over x to the 3rd power. I'm going to do this one real quick, and I want you guys to check my work. Well, I just learned the power rule, and the power rule says I should just take that power down front and make it 1 less. So I think the answer should be 1 over 3x squared. Does anybody disagree with me? Yeah, multiple people disagree with me. What did I do wrong?
The x cubed to the top.
Yeah, I don't have a rule on how to do derivatives of fractions yet. Just you wait, it'll come. But I don't have a rule for how to do the derivative of a fraction. I have a rule of how to do the derivative of x to some power. So the trick that I have to use on a problem like this is first to write it in a rule-friendly form. Okay, and that rule-friendly form is to write this instead as x to the power -3. So, allow me to emphasize, this is wrong. We cannot apply the rule this way. We have to write instead x to the -3 and then apply the rule as it is written. Now let me also ask, is it okay for it to be a negative power? Is that going to cause us any issues? I think it's okay. We just said that n should be some real number not equal to 0. Negative numbers count. All right, let me clean this up a little bit. So, what should the actual derivative be? Yes? Exactly. F of x should be equal to -3x to the -4. We made the power 1 less, but our power was already negative, so it just became more negative. That's what happened here. If I wanted to write it in a nice way, I would write -3 over x to the 4th power. It's more friendly for the eyes if we write it like that. Any questions about that problem? That was the first kind of tricky one I think we had to be careful about. No questions? All right, we'll move on then. All right, part C looks a little bit fishy right from the get-go. Do I have a rule on how to do the derivative of square roots? Not exactly. I have a rule for how to do the derivative of x to some power. Can I write a square root as a power? Yeah, what should the power be? Do you know?
1/2.
Yeah, it should be 1/2. So again, they're just trying to trick us by writing things in a funny way. So f prime of x, well, we're getting the hang of it now. All we have to do is multiply down the 1/2, and then x should be raised to the power of 1/2, but 1 less than that, which would just be -1/2. So if I wanted to write it in a nice way, I would write 1/2 times the square root of x. Something like that. Great. Okay. For part E, I think looking at this, I'm going to need to use 3 rules. Can somebody give me one of the rules that I'm going to have to use to do this derivative?
Power.
The power rule, that's number 1. I've got 2 more rules that I need to use. Anybody have another rule?
The linear function rule.
We're not quite going to apply the linear function rule directly, because as we can see here, we've got a quadratic term here. But the linear rule is kind of a combination of the power rule and one other rule. Do we think we're going to need to use the multiplication by constant rule? Would you guys believe me if I told you that x squared over 4 is the same as doing 1/4 times x squared? Yeah? Okay, that's good. It is true. So if we want to do the derivative of this, we're going to need to use the constant multiplier rule. The other rule we're going to need to use has to do with this sign here in the middle.
Additional.
Yeah, the addition rule. If we do the derivative of a sum, it's just the sum of the derivatives. So let me start. Since I know I can just do the derivative of both of these things individually, let me start with the right-hand side. I think it's going to be plus 0. That's what happens to the 3 when we do its derivative. And x squared over 4, well, that's just going to be 1/4 times the derivative of x squared, which is equal to, so this is all f prime of x. And the derivative of x squared is 2x, so I'll have 1/4 times 2x. I'm going to drop the plus 0. And if I do 1/4 times 2x, I get x over 2. So we're going to learn some more rules next time. Maybe we'll do it at the end of class today if I have time. We're going to learn some more rules, and then once Chase comes back, you'll learn even more rules. And all that derivatives are just combining all of these rules, which is why I think it's such an important skill to develop early on, how to look at these functions and see ahead of time which rules you're going to need to use. Okay? All right. Well, I'll run through a couple more of these. So next up, we've got f of x equals -3x to the -4. 2 rules I'm going to need to use for this problem. What are they? What's one?
Power.
Power rule again. The other rule?
Constant times a function.
Yes, constant times a function. So I'm just going to let the constant float, And then I'm going to multiply that times the derivative of the thing that the constant is being multiplied by. And I get 12x to the negative fifth. And if I wanted to write it in a nice way, I would write 12 over x to the power 5. So one kind of funny thing that I want to point out is that when we have these negative powers of x, my derivative will have a different sign than the original function. You'll notice that this function that's highlighted right now in salmon is a negative function, while this function down here that's the derivative of it, that's a positive function, at least for positive values of x. So this is just something that happens when we have a negative power. When we do that derivative, we introduced an extra minus sign right here. It came from the old power. When we multiplied down the old power, we got an extra negative sign in there. So that's why our derivative has a different sign. So if you wind up doing a problem about power rule with a negative power, that's one thing that you should probably check at the end is, okay, does my derivative have the opposite sign of the original function? If not, you may have dropped a negative. All right, great. All right, we'll do this one. So this is like a combination of some of the other things that I did. Right now, the way this is written is not rule-friendly. So the first order of business is to write it in a rule-friendly way. I don't know how to do the derivatives of either of these first two things. So I'm going to rewrite them in a rule-friendly way. I'm going to write this whole thing as x to the 1/3 power plus x to the negative second power minus 5x. And now I can apply the rule to each of these things. Okay? The sum rule also works for sums and differences of more than two terms. Okay? So we could have like x squared plus x to the 7th plus x to the 11th plus x to the 19 plus x to the whatever. Like, doesn't matter how many pluses we have. We just have to do the derivative of each individual summand. All right, so let's do it. What do we get? 1/3 x to the negative 2/3. That's what I get if I take 1/3 and subtract 1. Plus negative 2 x to the negative 3 minus 5. So if I wrote it in a nice way, I would write 1 over 3x to the 2/3 power. I wouldn't write a plus, I would write a minus. I got that extra minus sign from doing the power rule on a function with a negative power. So I get minus 2 over x cubed. Running out of space here. X cubed. Minus 5. And that would be my answer. So the new thing that we did here was, this time we had a sum of more than just two things. And I guess that was the only new thing that we did. We also wrote a third root as a 1/3 power. All right, we're going to skip h. I think h is easy at this point. If it's not easy, go to office hours or go to the SI session. That's what I recommend. Or stay after class or something. All right, let's do f of x equals x to the pi, though. I think this is a tricky one. F of x equals x to the pi. Is it possible to do? Yeah. Is there something that might confuse another student and make them think that it's not possible? Yeah, what's irking you?
The pi.
Yeah, the pi as a power. many students don't like pi because it doesn't look like a number when we write it like this. If instead I wrote x to the 3.141596 dot dot dot, then it would make a little bit more sense. So students often get tripped up by this pi thing. Don't let it happen to you. So the way I'm going to write it, its derivative, is just pi times x, and I have a really fancy way of writing the number that I get when I subtract 1 from pi. The way I write it is like this. Pi minus 1. That's what I write. Okay, so this is how we would do this derivative. All right, if you have some like mathematical constant like pi or e or whatever, don't bother trying to find some weird way of writing it. Just write that number minus 1. Perfectly fine. This describes exactly what number the power is. All right. So we did a whole bunch of derivatives using the power rule, using our constant rule, using our sum rule. Let me ask, which one did people think was the hardest one that we did? A through F, or no, A through I. What do we think? Does anybody have a strong opinion? Yeah?
D.
D was the hardest. Okay, so D was a little bit tricky. We had to, that was the first one that we did where we had to combine multiple rules. That was also the first one we did where we had a power that wasn't strictly an integer or a fraction. We had a decimal power. So two tricky things going on there. If I had to choose one that's the hardest, yeah, I'd be between, I don't know, I think G's pretty hard. Had to use a lot of rules. I guess what makes one hard for me is if you have to use lots of different rules, I think that makes it harder because you got to keep track of more things at a time. I'm not a multitasker. All right, great. Can we move on, or are there any questions about any of the things that we've done so far? Yes?
I just don't get through D, like what the D over the D of X means. Can you kind of just get rid of it?
Sure. So let's draw the attention to what she's talking about right there. So the question was, on this line here, we have a d dx of x squared, and on the next line, d dx isn't there anymore. Can someone answer her question and tell her where did it go? Yes?
Is it because you were finding the derivative of x squared?
Yes. So this d dx notation is a little bit confusing at first. What it really means is just do the derivative of whatever is in the parentheses. Okay? So it's kind of like if I had 3 squared, what this means is square whatever is inside the parentheses, right? And so on the next line, I might write 9. And so the square there went away because I performed the set of instructions that it has given me. And so I don't need to still do that anymore because I've already done it. So that's basically what's going on here. On this line, what's in the box says do the derivative of x squared. And what's in the box down here is what I get once I do it. Have I answered your question completely?
Yeah.
All right. Sweet. Thank you for asking. Any other questions? All right. So we had some nice drawings here. Okay, sweet. Application time. You guys have presumably done the section on finding the equation of a tangent line, right? This may be asking a lot, but does anybody remember the formula for the equation of the tangent line? That's okay, I wouldn't be brave enough to volunteer an answer when I was in freshman calculus, or first semester calculus, I should say. The formula is T of x is equal to f of a plus f prime of a times x minus a. Can I have a show of hands? Is this familiar? Ooh, not such a good showing. Okay. Well, let's talk about what it means. Okay. Let me put this in as simple terms as I can. This kind of looks like the equation of a line, which is in point slope form. Okay, that's kind of what's going on here. It's kind of like point slope form. If I was going to rearrange this, it would look like T of x minus f of a equals f prime of a times x minus a. And this kind of looks like y. This kind of looks like y minus y naught equals m times x minus x naught. Is that a familiar formula? Okay. Now remember what this formula kind of packages is that m is the slope of the line. In our case, the slope of the line will be the derivative at a. The other information that gets encoded when we write the equation of a line in point slope form is one of the points that's on the line. That's basically the information that we get here. We have m is the slope and x naught comma y naught is a point on the line. In our case, x naught is a and y naught is f of a. So this literally says line with slope f prime of a, which passes through the point a comma f of a. Great. Let's have a picture of what I'm talking about. So here's my f. And this is a. This point here would be the point a comma f of a. Remember, the height of the function is given by just plugging in your x value into this function, right? So the tangent line looks like this. Sort of. It's not going to be perfect. So the equation that I am going to highlight here in red, T of x is equal to this crap on the right hand side. It's a rearrangement of the equation of this red line, which we say, okay, The definition of the tangent line is that it goes through that point and it has the slope equal to the derivative. That's the definition of what the tangent line is. So there's a brief explanation of where that formula comes from. Any questions about that? That's a little bit abstract. All right, I highly recommend that you guys memorize this formula, which is highlighted in red. You'll probably have an exam problem at some point that says, find the equation of the tangent line to this function at this point. Or it'll say, use the tangent line to approximate f of x at some point. All right, great. So what's the takeaway? If we want to know the equation of the tangent line, which that's our goal in this problem, they say find the equation of the tangent line, there's 3 pieces of information I need to know. I need to know what the heck is A. So highlight in green. I need to know what the heck is A. I need to know what the heck is f of A. And I need to know what the heck is f prime of A. And if I know all of those 3 things, then I'll have my equation. So I need to find A. Ooh, that's a bad A. A. Oh, that's not much better. F of A. And f prime of A. Well, the first 2 things are pretty easy to find out. They tell us they want us to find the equation of the tangent line at x equals 1. Well, that's telling us A is equal to 1. Okay, so that's the first thing. F of A, I just get by taking A and I plug it into f of x. So f of A equals f of 1 equals 1 cubed plus 2 times 1 squared minus 5 times 1 plus 7. So if I add all that crap up, I get, what, 3 minus 5 is negative 2 plus 7 is 5. So f of A is equal to 5. I should just write it here. All right, now it's the part where I'm going to try to enlist your help. How do I figure out what f prime of A is? Can someone help me suggest a strategy for figuring out what f prime of 1 is? Yes?
Are you just finding the derivative?
Right, we're going to find the derivative of f, and then we're going to do something. Once we know what f prime is, how do I get f prime of 1? I just plug in, right? So to find f prime of 1, I first need to find out f prime of x. Well, if f of x is equal to x cubed plus 2x squared minus 5x plus 7. Somebody help me, I forgot how to find the derivative.
It would equal 3x squared plus 4x minus 5.
What about the 7?
0.
Yeah, derivative of 7 is 0, so that part just goes away. Perfect. So f prime of 1 is just going to be, well, 3 times 1 squared plus 4 times 1 minus 5 equals 7 minus 5 is 2. Great. So I've got f of A, f prime of A, and A. So my final answer will be, I just plug into what's highlighted in red. Okay, t of x is equal to f of A, I found was 5, plus f prime of A is 2, times x minus A. Well, remember a is 1, so in here is going to go x minus 1. And that is the equation of the tangent line. So, we had to do a little bit of work to find out the missing pieces in our formula. And we had to, before we even started that, we had to remember the formula. So, remembering the formula is probably the key step that you definitely need to remember. And then how to find these things is your next step. And then after that, it's just a matter of, connecting the dots, putting your pieces in the right place. All right, great. Any questions about problem number 3? Yes.
How did you go from 2x squared to 4x?
Great question. Who did the derivative for us? I think it was you in the cap. How'd you go from 2x squared to 4x? We're talking about this part here, 2x squared became 4x. Can you explain?
So you do the power rule and the constant times a function.
Yeah, power rule and constant times a function. Okay, so I'm gonna scroll down a little bit and dive into that. So we wanted to do d dx, aka do the derivative of 2x squared. The constant multiplier rule said that we can rewrite this as 2 times d dx of x squared, right? We can take that constant out. Remember, d dx just means do the derivative of what's inside the parentheses. So I can take that 2 right out front. And now, all I have to do is do the derivative of x squared, where I'm going to use the power rule. So I have a 2 times, now the derivative of x squared is 2x. So 2 times 2x is equal to 4x. Is that more clear, or would you like more details?
No, that's good.
Okay. Thanks for asking. Any other questions about this tangent line problem? It's a little bit long. Everybody feels like they could replicate it easily? Are you guys down for a quiz? No, I'm just kidding. Okay, sorry. All right. We'll move on. We'll talk about problem number 4. So, it says, the revenue in dollars from producing Q units is given by R of Q equals 1,000 Q minus 3Q squared. So, we have some kind of curvy-looking revenue function, and we're supposed to find and interpret R of 125 and R prime of 125. I think I'm going to need my calculator for this. So, let's start with R of 125. Well, I just plug in, right? R of 125 will just be equal to 1,000 times 125 minus 3 times 125 squared. 125 times 125 times 3. So I get 125,000 minus 46,875. 5,000 minus 46,875. I get $78,125. Okay, now comes the tricky part, computing R prime of 125. Who can help me? Just a first step is okay.
You gotta find R prime of Q.
Yeah, we have to find r prime of q first, and then we'll plug in. We'll worry about plugging later. First, we need to know r prime of q. So, I need to do the derivative of this function here, which is highlighted in green. I just do the derivative of the first part first. The first part is just linear, so the derivative of it will just be 1,000 minus the derivative of the second part. I use two rules to do the derivative of 3q squared. The first rule I use is the constant multiplier rule. I know that that 3 is just going to float along for the ride. And now what I need to write is the derivative of q squared, which is 2q. So, all in all, my answer is 1,000 minus 6q. Okay. So, we get 1,000 minus, now I'm going to plug in, well, okay, let me not write an equal sign there. Let's not be bad. Now I'm going to write r prime of 125. This amounts to plugging in 1,000 minus 3, sorry, that should be 6. 6 times 125, which is equal to 1,000 minus 750 equals 250. And the units are dollars per unit. Great, so we did the first part of finding these things. Now let's interpret them. So, question for the class. What does r of 125 equals 78,125 mean?
If you produce 125 units, you get $8,125.
Yeah, if you produce 125 units and sell them all, the amount of money that you get from the customer is $78,125. Now that's not going to be how much money you made. If you want to find out how much money you made, you'd have to take that number and subtract how much you paid to make them. Right? The cost of your supplies and labor and real estate, if you need real estate. Okay? So what this says is you sold 125 units for that price. Great. Some more tricky thing to interpret. What does it mean if r prime of 125 is equal to $250 per unit? Yes? Did you have an answer? No? Okay. The man in the cap has been helping me all day. Somebody else want to help me out? Pretty please?
Can you repeat the question?
Huh?
Can you repeat the question?
Yeah, the question is, what is the meaning of r prime of 125 equals $250 per unit? What does that mean in the context of the problem? I'm selling things. R prime is representing the rate of change of the R function. So what does it mean for my company in terms of dollars and cents?
The growth of the revenue at
Yeah.
that specific time.
Yeah, the derivative of the revenue at that specific time is equal to $250 per unit. What can that tell me about my business and maybe what I should do? hard question, I guess. Let me ask a smaller question. What does it mean if the derivative is positive? If I have a function and the derivative is positive, what does it mean for the function?
It's increasing.
Yes, it's an increasing function. So R prime of 125 units means if I increase my production from 125 units, the rate at which revenue increases is $250 per unit. Let me draw what that means. If our revenue function, maybe it looks like, I don't know, maybe it looks like this. Something like, no, it shouldn't look like that. It should look like this. What this is saying is that if I produce 125 units, then the slope of my tangent line is 250. Which means that as I increase production from 125 to maybe some higher number, the rate at which my revenue is increasing at that red point there is at a rate of $250 per unit. Which means we can expect probably, if we make, say, 126 units, the revenue is probably going to be pretty close to whatever our revenue was at 125 units plus 250. Okay? Later on, maybe our revenue function is a little bit curvier in a different kind of way. But right at this point, that's how fast revenue is growing. We like it when revenue is growing, by the way. That means we're bringing in more money. The key thing is that we want revenue to be growing at a faster rate than costs. Right? If revenue is growing and costs is growing but more slowly, then they're drifting further apart. If the revenue and cost are further and further apart, that means our profit margin is larger and larger. All right. I think I've beaten that into the ground. Questions about problem number 4? By the way, this is the marginal profit, marginal revenue. Okay, marginal revenue is when 125 units are produced, it's $250 per unit. So, any questions about the revenue problem? All right. We'll do problem number 5 then. Oops. All right, a baseball is thrown into the air. Straight up, I guess. The height h in meters as a function of time t in seconds after the baseball is thrown is given by this function f of t equals negative 4.9 t squared plus 25t plus 7. Okay? So, how should we do this? Okay, here's what we'll do. So basically what's happening is I'm standing here and I throw a ball directly upwards. So initially the ball goes straight up above my head. When it leaves my hand, it's going at a certain velocity. And as it keeps going up, 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 that speed at which it left my hand is decreasing. The ball is moving slower and slower and slower and slower until it hits the top, and it almost looks like it stands still for a second, and then it starts falling back down and bonks me right on the head. Okay? So that's what's happening here. So if we were to graph, for example, what this looks like, if we put time on this axis and height on this axis, which h is f of t, on this axis, well, at the start, it's at 0 meters off the ground, and then I throw it, and it goes higher and higher and higher, and then it hits its maximum height, and then time goes on, and for the rest of the time, it's actually falling. Okay? So I do want to point out, though, that this is not to say that I'm throwing the ball with this trajectory. I'm not throwing the ball with any horizontal velocity. I'm throwing it directly upwards, and it's falling directly back downwards onto my head, okay? But what this graph represents here is time is on this axis, okay? So if I'm here and I throw the ball, then at the pink point, it's in my, I just threw it. At the purple point, it's like this high. At the blue point here, it hits the maximum height. Then at the light blue point over here, it's back down on the same level as this purple thing. And then at the brown point, it's like getting kind of close to my head again. Okay, that's what's going on here. So if we want to know the baseball's velocity at t equals 2, well, this function, f of t, represents the distance between the ball and the ground. Does anybody know what is the relationship between the velocity function and the distance function? Yes? Exactly, right. The velocity function is just the derivative of the distance function. So v of t is equal to f prime of t. The way we get f prime of t is by using the power rule first on this first term. We get negative 4.9 times 2 times t. This class goes until 7:15, right? Okay. We'll finish this up real quick. So 2 times negative 4.9, I get negative 9.8 t plus 25. Okay, and then the 7 goes away because the derivative of a constant is just 0. So if I want to know what is the baseball's velocity at time t equals 2, I just plug in 2. V of 2 is just going to be equal to negative 9.8 times 2 plus 25, which is, let's see here, negative 19.6 plus 25 equals 5.4. Hope I did that right. And the units would be meters per second. Fairly straightforward. Are there any questions? Okay, the thing to remember here is that the velocity function is given by the derivative of the distance function. And if we wanted to know the baseball's acceleration at time t equals 2, does anybody know the relationship between the acceleration function and the distance function? Yeah. Yeah, the acceleration function is given by the second derivative of the distance function. So a of t, a stands for acceleration, is equal to the derivative of the velocity. How is our speed changing? That's basically what it's saying. And that's equal to the second derivative of f. And that is all equal to the derivative of this function highlighted in red. It's a linear function. The derivative is just negative 9.8. So what's a of 2? If I plug in 2 into the function negative 9.8, what do I get? Yeah, just negative 9.8. It's just a constant function. No matter what I plug in, the acceleration is 9.8 meters per second squared. If you've taken a high school physics class, you probably know that number. That's the acceleration due to gravity. That's what we're all feeling right now. All right, great. That's it for today. Thanks for coming. Hopefully you learned something. And yeah.